What we just finished talking about with the fundamental theorem of line integrals is how do we make difficult integration or difficult work actually easier utilizing mathematics. So if I know something or I have a theorem that I can utilize that will actually make my work easier, I should go to use that, right? It's actually one of the fundamental ideas of mathematics. That is that we want to make things a lot simpler. We want to make them more elegant. We want to actually decrease the amount of work that we're doing, and we want to use our creativity and our minds in order to do that. What we're going to look at today is something called Green's theorem. And Green's theorem is a relationship between the a line integral and the double integral, okay, that will allow us to actually do line integrals a lot more simply, or it might allow us to do double integrals a lot more simply, just depending upon, which one we choose, right? And so it's basically like this kind of this idea of how do we go in and set up a problem, okay, based upon what we know about it, in order to give us the easiest way to solve that problem, okay? And that's what Green's theorem is going to do for us. So it's another option, right? So this whole chapter is actually really great for that, because on the one hand, you got the fundamental theorem of line integrals, which makes doing line integrals a lot easier. And now we've got Green's theorem, which is going to make doing line integrals or double integrals a lot easier as well. So the fundamental theorem of line integral states that if f is conservative, then the line integral of f dot dr on a curve C is going to end up equaling f of r of b minus f of r of a for f such that del f is equal to f and the curve r of t with a less than or equal to t less than or equal to b. So basically what this is saying is that if we have that we have a vector field f and we actually construct a potential function from f, right, because f is conservative, then all we've got to do is we've actually just basically got to go in and calculate the value of the potential function at its endpoints, right? So we imagine that we've got we've got our conservative vector field, whatever it looks like. So here's our vector field, okay? Here's f, and I've got my curve, okay? And I've got my curve, and as long as it's simple, connected, right? We have some other things that we need, but like say that that's the curve. Then all I need to do is I just need to figure out what this is here. So we call it we'll call this f of that's f of r of a and f of r of b, okay? And it doesn't actually, in this case, it doesn't actually matter what the path is, okay? It doesn't matter what that path is. We can use any path that we want. And so basically what that does is it takes this two-dimensional problem that we have, which is finding the value of the field over a two-dimensional space. That's the entirety of the field, or on that curve, and it reduces it to finding it at its endpoints, at the boundaries, right? We can think of f of r of a and f of r of b, right, these endpoints of our curve, as boundaries of the curve. And so we're going to do that, or we're going to work with a similar idea when we work with Green's theorem. What Green's theorem is going to do is it's going to say, okay, so I've got an area now, and instead of working with the area, or instead of finding the entirety of the integral on the area, what I'm going to do is I'm going to actually just look at or figure out what the value is around its boundary. Okay, so let me kind of give you a little demonstration of that. So what we want to do for Green's theorem, all right, it's going to be a similar idea except in a different dimension, is we're going to imagine that we've got a simply connected curve, or excuse me, a simply connected region, right? So here's our region, we'll call that region D. And it's got a boundary curve, okay? And that boundary curve is, it's closed, it's a closed curve. It's simple again, we don't have any kind of like overlap, we're not crossing over ourselves, okay? So we've got this region D, and it's in a field. So like we'll imagine it's got like this force field of some sort. We've got all these, these field values in the region. Now the boundary around D, okay? So the boundary around D is some curve C. I've got a curve C around D, okay? And what Green's theorem is going to say is that as long as I have, right, an open, simply connected region and a boundary curve C, that's, again, piecewise smooth, simple, right, that sort of thing, then I'm going to end up with this. I'm going to end up with the line integral of C of f dot dr, okay, so basically the calculation of the work is going to equal, and again, C of p dx plus q dy. All right, that's our standard form there. And that's going to end up equaling then the double integral on d of qx minus py. So what it does is it reduces our double integral to a line integral, in case that line integral is really simple to work with, or we can take a line integral that maybe is more complicated and transform it into a double integral. Okay? So either we can calculate the double integral, we can calculate the area and then this q dx p of y, right, around this region, that line integral. Or we can, excuse me, not the line integral, but around that region we can figure out what the value of this integral is. Or we can calculate the line integral by actually figuring out what the second partial with respect to x and the second partial with respect to y for q and p, and times basically the area of the figure. And so essentially, again, we're just kind of like doing some conversion. If we have the right characteristics with the right qualities, okay, then we're going to actually be able to make this conversion. And what you'll notice here is that the area, so if your area is D, the boundary of the area is C. So basically what it's doing here is something very similar to the fundamental theorem of line integrals, or even the fundamental theorem of calculus. We're actually figuring out the value of an entirety of a figure or a curve based upon only its boundary. So let's look at, this thing is called Green's theorem. This is the circulation form. And so we're going to let D be an open, simply connected region with a boundary curve C that is piecewise smooth, simple, closed curve, oriented counterclockwise. Okay, so we do need that orientation to be counterclockwise, a counterclockwise orientation. If you have a clockwise orientation, multiply by -1, make it counterclockwise. Let F equal PQ be a vector field with the component functions that have continuous partial derivatives on D. Then the line integral, C of f dot dr, is going to equal the line integral on C of p dx plus q dy, and that's the double integral on the region D, whatever region D that we have, of qx minus py. So that is the partial of q with respect to x minus the partial of the partial of p with respect to y. So let's ask ourselves an interesting question about this. So basically what this is saying is saying, okay, we've got an easier way to go out and calculate this. Like say, for example, if the region is really easy to kind of, create its area, we might want to use that double integral, right? Or if we have a double integral and could figure out values of q and p, we might want to go back to using f dot dr. So let's think about this now from the perspective of a conservative vector field. So this is an interesting question here, all right? Suppose that we have a closed curve in a conservative vector field. So now we've got a closed curve inside of a conservative vector field. What is the value of the line integral over that curve in that field? So what we're thinking about here is we're saying to ourselves, okay, well, do I really want to calculate that? I don't necessarily have to, all right? I don't necessarily have to, and Green's theorem actually shows me how it is that I don't have to. So if you remember, I have a conservative vector field. So according to the fundamental theorem of line integrals, the integral C of f dot dr, okay, is going to equal this, C of p dx plus q dy. But since the vector field actually happens to be conservative, we know that q of x equals p of y. Okay, remember p is the function with it's basically our x component, q is our y component, and because it's a conservative vector field, remember the test for conservative vector fields actually has that their mixed partials will equal each other. So this actually ends up equaling, by Green's theorem, we've got the area of D, and we've got qx minus py dA, but since qx and py actually happen to equal 0, this is going to end up equaling 0. So what this tells me is that if I have a conservative vector field and a closed curve, okay, then what the value of that line integral over that closed curve is going to end up equaling 0. Which makes sense because basically what's happened is that you really pretty much haven't gone anywhere. All right? Like we calculated the work going out to wherever the farthest is that we have on the side of the curve, but then we head backwards, right? And we essentially subtract out everything that we added in. All right? And so this is actually kind of an interesting or a neat occurrence that happens as a result of the fundamental theorem of line integral and Green's theorem. Another thing to note as well is that Green's theorem only works in 2 dimensions. It's not a 3-dimensional theorem. So we have to actually be aware that we're not actually going to be able to go in and utilize this particular fact for 3-dimensional. Let's take a look at some examples. So let's suppose we want to calculate the line integral around C of x squared y dx plus y minus 3 dy, where C is the rectangle with vertices 1, 1, 4, 1, 4, 5, and 1, 5. Now, we could go in, actually, you can actually take a look here, and this is not a conservative vector field, okay? Not a conservative vector field. The derivative with respect to y of x squared y is x squared, and the derivative with respect to x of y minus 3 is 0. So consequently, not conservative. We can actually see that that's the case. So we're not going to be using the fundamental theorem of line integrals here. Consequently, we'd have to actually go in and parametrize all of the sides of the curve. We'd have to go in, find the parametrization of all the sides of the curve, then take the integral of all 4 of the sides. But what we can notice here, or what we can see here is that what we do have is we have a simple closed curve, okay? And we also have a simply connected region, and so consequently we can use Green's theorem. And the area of this thing is way easier to figure out, okay? If we actually figure out what our integral is here for this region, okay, what we're going to get is we're going to get a bounds, and our bounds is going to have, we're going to have y is going to go from 1 to 5, and x is going to go from 1 to 4. So there's the bounds for our integral, and that actually gives me the entirety of the integral for this particular rectangle. Rectangle is being kind of simple to work with. Now all we need by Green's theorem is remember that this thing is going to end up being the double integral over the region D of q of x minus py. So I look here, I look at qx, so q is y minus 3. Okay, so I'm going to put q of x, q equals y minus 3. So qx is going to equal 0. And py is going to end up equaling x squared. Okay, because p is x squared y, just like we've had that before. So consequently, we're looking at the double integral over x squared dy dx. And so you can go in, this is pretty straightforward double integral. Go calculate your double integral. Notice how much easier that is than going through and parameterizing all 4 sides of the rectangle, right? We don't want to do that. We'd prefer to just go in and calculate this relatively simple double integral. So let's take a look at another example. Let's say we want to calculate the work done on a particle by a force field f of xy equals y plus sine x and e to the y minus x. As the particle traverses x squared plus y squared equals 4, exactly once in the counterclockwise direction, starting and ending at 2, 0. So what we have here is we have, we're going to have this line integral, okay, over C, and it's going to be f dot dr because we're looking for the work. And we know that that's going to equal the integral over C of p dx plus q dy, which in this case is going to be the integral, the line integral around our curve of y plus sine x dx plus e to the y minus x dy, okay? Now, I'm going to look at the region here, and the region, we're going to draw a picture of it, is going to look like, right, it's a circle of radius 4, oriented counterclockwise, okay? And it traverses it only once, so we've got that, that important piece there that the line integrals, we're only going to go around it once, that's good. And also that we're oriented counterclockwise, so we have the simply connected region, and that's D, okay, that's the circle. We have the closed curve, which is also a circle, but not filled in, okay, C, and it's a simple closed curve, just like we needed, oriented counterclockwise, and we traverse it only once. So we can use Green's. So we look here, And the first thing I want to notice is I want to say, okay, well, is this conservative? Let's actually go in. We'll find q of x. Qx is equal to -1. Py is going to equal 1. Okay, so we got qx equals -1. Py is going to equal 1. And so, consequently, the two of them are not equal. This is not a conservative vector field. And so, it's not equal identically to 0, but take a look. Remember, Green's theorem says that this whole thing is going to equal the double integral over the region D, okay, of q of x minus p of y dA. So this ends up equaling the double integral of d of -2, right? Because it's going to end up being -1 minus 1, so -2 dA. So now what we want to do is let's go in and we've got the double integral over our region D of -2 dA. And this is going to then equal the double integral around the region E, and then so we can take -2, we'll pull that out, and it's just dA. Okay, so this is just the region, the area of this circle right there. Now that's a circle of radius 2. Okay, so the area of this region is actually pi times 2 squared, which equals 4 pi. So the value of this line integral ends up being -2 times 4 pi, which equals -8 pi. And that is the value for your line integral. So notice that because we have this simply closed connected curve, okay, that we can actually simplify this line integral quite dramatically by using Green's theorem, right? We didn't even actually have to go in and integrate. We just had to know, hey, look, that's just the area, right? And that's, of course, that's because we have a constant here. It just made our lives a lot. So let's take a look at a third example. Let's suppose we want to find the line integral around a curve C of sine x squared dx plus 3x minus y dy. You can tell that that's not a conservative vector field, by the way. Go ahead and figure that out on your own. Where C is the right triangle with vertices -1, 2, 4, 2, and 4, 5, oriented counterclockwise. So what we're going to be doing here is we've got this triangle, and let's go in and like actually draw it, or draw, kind of create a little bit of a sketch. Okay, it's going to go -1, 2, and then 4, 2, 4, 2, and then we go to 4, 5. So it's a right triangle. Oh, that makes life easy, doesn't it? And since, I just saw before, I'm actually going to want to figure out what the area is of this, just in case I need it, because I will, or I might. And so this is 3, and this piece right here, right, because it's 5 minus 2, and this is going to end up being 5 because it's 4 minus a -1. So the area of the triangle is equal to 3 times 5, which equals 15. So this is a simple closed curve, right? It's piecewise smooth, meaning that we can break it up, but like each point connects with each other point. So that's what we mean by piecewise smooth. It's not like, out in nowhere. We have a simply connected region here, which is the triangle, inside of some kind of vector field, right? We can kind of imagine, oh, here's my vector field. And so we're going to use Green's then. And so we've got the double integral around the region D. And I'm not going to worry about the region D right now yet. And I want qx minus py, and this is going to then be dA. Okay? Qx is going to end up equaling 3, and py is going to end up equaling 0, right? Because there are no y's instead of sine of x squared. So this is going to end up equaling the double integral over the region D of 3 minus 0 dA, which is just the double integral over D of 3 dA. Well, we got the same issue that we had in the last time. We got the 3 times the double integral over the region D of dA. And so this ends up equaling 3 times, this is just the area of the triangle. So that's A of t. So this is 3 times 15, which equals 45. And that is the work done over that region, or that's the value of the line integral. Let's suppose now that we want to calculate the area enclosed by this ellipse, x squared over a squared plus y squared over b squared equal to 1. So we've got the ellipse, not the greatest drawing, my bad, but well, there it is. I just want to illustrate. So we've got, you can see we've got 0b, 0 negative b on the bottom, negative a0, a0. And what I want to notice is we want to actually find the area. Now, Green's theorem right, relates the integral of p dx plus q dy along the boundary, right? Along the boundary of this particular ellipse is going to equal the double integral d, okay, of qx minus py dA. Okay? So the challenge that we're going to have is we want to find this area, and utilizing like that double integral to find the area might be actually like prohibitively difficult. But it might be a lot easier for us to actually go through and calculate, okay, to go through it and calculate the value along the boundary of the curve utilizing PDX and QDY. So the area of this region, okay, is going to end up equaling the double integral over d of just dA. So what that means is that we're going to need that qx minus py is going to have to equal 1. So we're going to need some appropriate values for, or appropriate function. We're going to need an appropriate function for q and p to allow this to happen. Okay? And we're going to need, essentially, like we are for any situation, we're going to need an appropriate parameterization for the ellipse. So the parameterization for the ellipse, just in general, you may remember this from your Calc 2, but we're going to remind you, is going to end up being x equals a cosine t and y equals b sine t. Okay, for 0 less than or equal to t less than or equal to 2 pi. So now what we need is we need to figure out what q of x is and p of, what q of xy is and what p of xy is. So I need those two when I subtract them to equal 1. So we're going to suggest that if I take p of xy equal to negative y over 2 and q of xy equal to x over 2, that when I take q of x minus p of y, I'm going to end up getting 1. And so let's see if that's the case. I got p of y is going to equal negative 1/2. Q of x is equal to 1/2. So qx minus py is equal to 1/2 minus negative 1/2, which equals 1. What that means is that my double integral over d, okay, of qx minus py dA is just equal to then the integral, or it's just equal to the area of the region, right? So this equation, what we've done by utilizing this force field of negative y over 2 and y over 2 is we've ended up actually creating a function for our area using the line integral, okay? So I'm going to back that out, and I'm going to take it back up here to this line integral here, the PDX and QDY. So that means that the integral, the double integral of d over d of dA is just going to equal the line integral around its boundary of, in this case, negative y over 2 dx plus x over 2 dy, and that equals the line integral over the boundary of 1/2 times the line integral over the boundary of negative y dx plus x dy. And that's the line integral version. So it's the line integral for the area of a region. That's cool. So if we have a proper parameterization for a region, okay, we can go out and actually utilize this line integral, and it can make life a lot easier, which it will in this case. Okay, so now I've got 1/2 times that value. I'm going to go back up. I'm going to go back up to my parameterization. I've got x equals a cosine t and y equals b sine t. Okay, so dx, okay, is going to equal negative a sine t dt, and dy is thus going to equal b cosine t dt. We are going to be, of course, integrating over 0 to 2 pi, so my new integral, the double integral of d dA, that area, is going to equal 1/2 times the integral from 0 to 2 pi of negative y, so negative b sine t times negative a sine t, and we're going to pull the dt at the end, plus a cosine t, b cosine t, all of this dt. This is thus going to equal 1/2 times the integral from 0 to 2 pi of, and this will just be ab sine squared t plus ab cosine squared t dt, which equals 1/2 times the integral 0 to 2 pi of ab dt. So this is 1/2 ab evaluated from 0 to 2 pi, or abt evaluated from 0 to 2 pi. So that's equal to 1/2 times 2 pi ab. So the formula for the area of an ellipse is pi ab. And there we go. So, a couple things. I mean, one, hey, cool, I found the area of an ellipse. Not the big point. The big point is this right here, okay? That using, if we have a closed curve, right, simply connected curve oriented counterclockwise, traversed only once, then the double integral of d over an area dA is equal to 1/2 the line integral of negative y dx plus x dy. All right, let's use that actually because it's really handy, really powerful. Now what we want to look at is we want to look at an easier way to find flux utilizing Green's theorem. So recall that the equation for flux is going to end up being the line integral of f dot n ds, where n is the normal vectors of the boundary curve. Okay, and so if we have f equal to pq, all right, and they have a partial continuous derivatives on an open region containing d, we've got this piecewise smooth curve, we've got a simply connected region, then what we're going to get is that the flux, so that's our flux here, can be transformed into a double integral with px plus qy dA. Okay, so let's actually just go through and we'll do a brief sketch of a proof here, because we just want to relate this to what we've been doing thus far. So if you remember, we've got f dot n ds, and that's going to end up equaling the line integral of c, and we have it negative q dx plus p dy. Okay, where q and p are exactly the ones that we've been using when we talked about the f before. All right, and so what we'll do is we'll use just a change of variables. We're going to say that m is going to equal negative q, and we'll let n equal p. Okay, so this integral right here, the integral of negative q dx plus p dy, is going to end up equaling a line integral over c of m dx plus n dy. Okay? Then, by the circulation formula for Green's theorem, this is going to be then the double integral of over a region D of nx minus my dA, right? Just substituting in, notice n is my q, m is my p in this case, okay? So this is then going to equal, well, n, remember, is p, so this is going to be, this is going to end up being then px minus negative qy, with the double integral dA, and so this will end up equaling the double integral over d of px plus qy, which is exactly what we got right here. All right, so let's suppose that C is the circle with radius 5, centered at the origin, and let f of xy equal xy. So we want to calculate now the flux across C. So we'll use that the integral of f dot n ds, right, our flux, is going to equal the double integral across, around the region D of, and this will be px dy plus, px plus qy dA. So if we go in, we can see that px is going to equal 1, qy is going to equal 1. So this gives me the double integral over the region D, okay, of 2 dA, which is going to equal 2 times the double integral over d of dA, right? This is the area of the circle, okay? Area of the circle, so this is going to equal 2 times pi times 5 squared, which equals 50 pi. Done. Flux was easy that way, right? So much easier to calculate flux that way than it is to go out and find the line integral, okay? Because px plus qy is such a simple equation to integrate. So let's take a look at another flux example. Let's look at an application. So let's suppose that water flows from a spring located at the origin, and the velocity of the water is modeled by a vector field v of xy equaling 5x plus y, x plus 3y meters per second. So we want to find the amount of water per second that flows across the rectangle with vertices -1, -2, 1, -2, 1, 3, and -1, 3. Okay. Once again, we're going to be looking for region of C, okay, around, and we're looking for f dot nds because we are looking for the flux. And so that's going to equal the double integral of px plus qy dA over the region D. Now the region D is a simple connected region, counterclockwise orientation. In addition to that, it's a rectangle. So its area is going to be pretty simple to figure out. We won't have that much of a problem with the area, finding out the area. So what I need to do is I need to go in here and I'm going to first find px. So px is going to equal the derivative of 5x plus y, so it's going to equal 5. And qy is going to equal the derivative of x plus 3y, so it's going to end up equaling 3. So px plus qy is going to equal 5 plus 3, which equals 8. So we're now looking at the double integral over the region of 8 dA, which is just equal to 8 times the double integral over the region D of dA. Well, that's the area of the rectangle, okay? So in this case, we don't actually have to go in and do any integration. I can just look at this and I could say, okay, well, the length of this side here is going to end up being 2. The length of this side is 5. So this is going to end up equaling 10. So this is 8 times 2, 10 times 2, which equals 20 times 8, which equals 160. And that is the flux. This is going to be in meters squared per second. And there we are. Okay. So notice again, because we have a simple closed region, it turns out also because we have px plus qy ends up being a constant. All right. We can pull the constant out and just find the area of the region D. Okay. All right. So let's kind of summarize what we've talked about a little bit. So Green's theorem for simply connected regions, let's kind of summarize this a little bit. So Green's theorem can be used if we have a simply connected region D surrounded by a simple closed curve C that's oriented counterclockwise and only traversed once. Green's theorem only works in 2 dimensions, so we're only going to be using this one in 2 dimensions. And the line integral of the closed curve on a conservative vector field ends up being 0 because remember, right, when we're using Green's theorem, right, we're basically using py minus qx. Those two are equal to each other. So on a conservative vector field, everything zeroes out. Green's theorem is going to allow us to convert complicated line integrals over non-conservative regions to double integrals that will be much simpler to solve. So that's the whole point. What we want to do is we want to actually go and make our lives easier. We want to make finding these integrals easier to solve. Okay, and we can also convert area problems into line integrals by using this particular equation. The double integral of dA, which is the area, so that's our area, will equal 1/2 the integral over C of -y dx plus x dy, where C is the boundary of the region D. We also have a flux version of Green's theorem that simplifies the process of finding flux in 2 dimensions as well. So that actually kind of completes how we're thinking about Green's theorem. Green's theorem is very powerful, can make life a lot easier. You might notice that this feels just so much easier than finding double integrals or finding complicated line integrals. And that's the point of Green's theorem.